We're now on to lesson number 5 of the Counting Principles chapter. And for lesson number 5, we'll be looking at Pascal's triangle. Alright, so let's take a look at Pascal's triangle. So in this diagram right here, as you can see, this resembles the shape of a triangle. And for Pascal's triangle, this will be like a mathematical model that we can use to solve counting problems. So let's just try to break down what Pascal's triangle is. Now, when we have the triangle, we generally begin with 3 ones on the top. So here's a 1 here, a 1 there, and a 1 there. And then we're going to try to construct the rest of the triangle here. Alright, so each number is the sum of the values directly above. So, well, every single number on the outside will be a 1. So everything here will be a 1. Everything here will be a 1, and then we'll use this rule when we're more dealing with numbers in the middle. Alright, so that's a 1. Now 1 plus 1 would mean this is 2, and this number here will be a 1. Once again, this number will be a 1, and then a 1 plus 2 will be 3, 2 plus 1 will be 3, and this outside number here will be a 1. Alright, great. So continuing on with the pattern here, the outside numbers will be 1. The inside numbers will be the sum of the values directly above. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 will be 4. And we'll have 1 on the outside here. Alright, so I think generating the rest of the triangle won't be too hard. So let me just quickly generate the numbers here. 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, 1 on the outside. Then we get 1, 6, 15, 20, 15, 6, and 1. So like 10 and 5 would be 15, 10 and 10 will be 20. There's the next line, the next row, the next row, and the next row. Alright, so this is Pascal's triangle. And for today's lesson, we'll be using this to solve some of the counting problems that we encountered early in this chapter. And then we'll use Pascal's triangle for the next lesson as well. Alright, so how is this connected to combinations? Well, Pascal's triangle with combinations NCR, let's take a look here. At the very top, we know the value of Pascal's triangle at the very top will be 1. And if you have 0, choose 0, well, that's going to be 1. And then if I work over here, this is going to be 1, choose 0. So basically 0 goes from 0 to 1. And this will be 1, choose 1. Okay, so moving on, this will be 2, choose 0. This will be 2, choose 1. And this will probably be, well, we go from 0 to 1 to 2, choose 2. Okay, so you might see a little pattern here. I mean, I have a 0 there, a 1 there, a 2 there. So I'm assuming that this will probably be a 3. This is choose 0, choose 0, choose 0. So this is probably going to be a choose 0, 3, choose 0. And then if we look at the second row here, we went from 2, choose 0 to 2, choose 1 to 2, choose 2. So this is probably going to be 3, choose 1, 3, choose 2, and 3, choose 3. Alright, so this will be 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. 5, choose 0, 5, choose 1, 5, choose 2, 5, choose 3, 5, choose 4, and 5, choose 5. The last row will be 6, choose 0, 6, choose 1, 6, choose 2, 6, choose 3, 6, choose 4, 5, and 6. Alright, so this is how Pascal's triangle is directly related to combinations. So each row corresponds with the value of n. Begin with n equals to 0 at the top. So this is n equals to 0 at the top. This is n equals to 1, n equals to 2, n equals to 3, n equals to 4, 5, and 6. Each diagonal column corresponds with the value of r beginning with r equals to 0. Alright, so for every single diagonal here, your r value will be 0. And then the next row over in this column, or this diagonal row here, the r values will be 1. And the next row over, the diagonals will be 2, then 3, then 4, 5, and 6. That's r equals to 1, r equals to 2, r equals to 3, 4, 5, and 6. The nth row will have n plus 1 columns. So when n equals to 5, which is this case right here, there will be 6 diagonal columns. So 1, 2, 3, 4, 5, 6. All right. So that is Pascal's triangle with combinations. Let's move on now. All right, so let's look into the Pascal's triangle a little bit more. Let's analyze the triangle a little bit more now, and let's try to make some connections with the patterns and combinations a little bit more. So there is a symmetrical pattern in Pascal's triangle. The opposite sides of the triangle are equal. So what does that mean? Well, that means if I have a 1 over here, then on the opposite side, it's also equal to 1. If I have a 1 over here, then on the opposite side, it also equals to 1. All right. So what that means is if this is 1, choose 0, then this is also going to be, well, this is equal to 1 and that's equal to 1. And if this block right here represents 1, choose 0, and this represents 1, choose 1, then 1, choose 0 equals to 1, choose 1. Over here I have 2, choose 0, and over here this is going to be 2, choose 2, but since they're both equal to 1, then these two expressions are equal. And over here I have 3, choose 0 equals to 3, choose 3. This represents 3, choose 3. And these two numbers are also equal, so this is going to be 3, choose 1. And this will be 3, choose 2, so these two expressions are also equal. This expression and that expression will have 4, choose 0 and 4, choose 4, so those expressions are equal. And you'll also notice that the 4's are equal, so what does that mean? 4, choose 1 is equal to 4, choose 3. So based on the pattern here, you should be able to come out with a conclusion here. We got 5, choose 0 equals to 5, choose 5. 5, choose 1, which is this expression right here, or sorry, this number right there, and 5, choose 4 is this number right here, so those two are equal. And we also have 5, choose 2 equal to 5, choose 3, which is this is 5, choose 2, and this is 5, choose 3. All right, so there is a general formula for this pattern here, this symmetrical pattern, and that is n choose r equals to n choose n minus r. Okay, so if I take a look at an example right here, if I have 5, choose 0 here, 5 is my n, 0 is my r, and that's going to equal to 5, which is my n, and n minus r in this case is simply going to be 5 minus 0, which equals to this expression right there, and that represents n minus r. So n choose r is equal to n choose n minus r, and we can use Pascal's triangle to verify that. All right, let's take a look at another example here of a recursive pattern. Each term is the sum of two terms directly above. If there is only one term above, then they will be equal. All right, so I know this this one here and this one here. If I add them together, I get 2. So 1 choose 0 plus 1 choose 1, that's going to equal to 2, which is going to be 2 choose 1. So this yellow box right here represents 2 choose 1. All right, we have 3 plus 1 gives you 4. So this 3 represents 3 choose 2, and this 1 represents 3 choose 3. And if I add those together, I get 4. And 4 is represented by 4 choose 3. So the 4 in this situation is 4 choose 3. Let's take a look at maybe a few more here. 4 plus 6 gives me 10. So this right here is going to, well, this is 4 choose 0, so this will be 4 choose 1, and this will be 4 choose 2. So 4 choose 1 plus 4 choose 2, that will equal to 10. And this 10 will be, well, this is 5 choose 0, 5 choose 1, and this will be 5 choose 2. All right, so hopefully we're seeing a little pattern here. Let's just keep on going. The general formula for this recursive pattern is that if I have n choose r, which is this case right here, n choose r, plus n choose r plus 1, that's going to equal to n plus 1 equals to c of r plus 1. All right, so that's a little formula right there that we can come up with by looking at Pascal's triangle. All right, let's move on. Now, the kind of problems that you will use Pascal's triangle for this chapter, they will be directly involved with the pathway problems. So whenever we have a pathway problems, it's a lot easier to solve the pathway problems by using Pascal's triangle instead of using the permutations method that we learned back in lesson number 2, I believe. And when we have these awkward shapes, like we have in this second example here, it's definitely a lot easier to solve this problem using Pascal's triangle. So Pascal's triangle is very useful for the pathway problems, and let's take a look here. So if I take my first example and if I kind of rotate it into a triangle shape so that this looks very similar to Pascal's triangle, I can start applying the the numbers from Pascal's triangle in order to get the number of pathways from A to B. Now, if I go from here to here, there's only one way to do that, going from A to this point. That's one way. And if I want to go from here to here, there's only one way to do that as well. So that's going to be a 1. If I want to go from here to here, that's also going to be one way. Remember, you can only go in one direction. I mean, to get to this point, I can't go like this way, this way, this way, and that way. I can't do that. Just you got to take the least number of paths to get down to here, so there's only one way to go from here to here. And then if I have 1 plus 1, that's going to be 2. There's 2 ways to get to this point. So this 2 represents going from here to there. That's one way of doing it. And you can also go from here to there. That'll be 2. Or you can simply add these two numbers just like we did in Pascal's triangle, and you'll get 2. And everything on the outside is simply going to be a 1. A 1. 1 plus 2 will be 3. 2 plus 1 will be 3. That will be a 1. This will be a 1. 1 plus 3 will be 4. 3 plus 3 will be 6. 3 plus 1 will be 4. And 1 on the outside again. There's a 1 over here. 1 plus 4 will be 5. 4 plus 6 will be 10. 6 plus 4 will be 10. 4 plus 1 will be 5. All right, 1 plus 5 will be 6. 5 plus 10 will be 15. 10 plus 10 will be 20. And 10 plus 5 will be 15. And we just continue the pattern there. There's going to be 21. That's going to be 35. That's going to be 35. 21 plus 35 will be 56. 35 plus 35 is 70. And finally, to get this final point B, we do 56 plus 70. And that's going to give you 126 ways from A to B. All right, so Pascal's triangle is definitely useful for the pathway problems. Now let's take a look at more of a challenging problem here. I'm going to rotate this into a shape of a triangle. And let's just continue the pattern here where everything on the outside will be a 1. So we can always start with that. There's a 1 there, a 1 there, a 1 there. 1 plus 1 is 2. A 1 there on the outside. A 1 there on the left-hand side. 1 plus 2 will be 3. 2 plus 1 is 3. And then we also have a 1 over here. And then we're going to continue on the other side. 1 plus 3 is going to be 4. 3 plus 3 will be 6. 3 plus 1 will be 4. And there's also one way over here. All right, good. 4 plus 6 will be 10. 6 plus 4 will be 10. And 4 plus 1 will be 5. Now, over here, there's 10 ways to get to this point. So if there's 10 ways to get to that point, and in order to get to the next point here, this will also be 10. Because if there's 10 ways to get to this point, there's only one point from here to here, so those 10 ways will also qualify for 10 ways over here. So this has to be a 10. 10 plus 10 will be 20. 10 plus 5 will be 15. This will also be 10. And then 10 plus 20 will be 30. 20 plus 15 will be 35. And if there's 15 ways to get to this point, and if there's only one point from here to here, in order to get through here, you must go through that point. So if this is 15, this also has to be 15. All right, 10 plus 30 will be 20. Or sorry, 10 plus 30 is 40. 10 plus 35 is 65. That's going to be 50. This will be 15 as well. And then we just continue the pattern here, adding the numbers adding the numbers, adding the numbers, adding the numbers again. Now if there's 220 ways at this point, then this point will also be 220 ways. Then we add these two numbers together, then we get 400. If there's 400 ways here, there must be, well, let's add these numbers first, and then we get 520. And if there's 400 ways to this point, then this point will also be 400. So finally, to get point B, we just add 520 to 400, and we get a total of 1,020 ways from A to B. All right, let's take a look at another example here. In the game of checkers, you can only go forward by moving diagonally to the left or the right. With the following checker, I guess the following checkerboard here, how many ways are there to reach the other side? All right, so how many ways are there to reach the other side? Okay, that's an interesting problem here. So let's try to set this problem up just like Pascal's triangle. So from here to here, there's only one way. From here to here, there's also one way. From here to here, we must go through, here, then there, so that's also going to be one way. 1 plus 1 will be 2. And if there's one way here, then go from here to here, this will also be one way. Remember, everything on the outside will always be 1. All right, so that's 1, this will be 1. 1 plus 2 will be 3. 2 plus 1 will be 3. And this one will just move over. 1 plus 3 is going to be 4. 3 plus 3 will be 6. 3 plus 1 will be 4. And this 1 will just move over to that side to be 1. This 4 will, if there's 4 ways to get to this point, and we can only get to this point by going through that point, so if this is 4, this will also be 4. 4 plus 6 will be 10. 6 plus 4 will be 10. 4 plus 1 will be 5. All right, 4 plus 10 will be 14. 10 and 10 is 20. 10 and 5 is 15. And if there's 5 ways to get to this point, and once again, if you want to get to this point over here, the only way to get to this point is to go through this point. And if there's 5 ways here, then that means there's also going to be 5 ways to that point. Using the same theory here, if there's 14 ways to get to this point, then this point must also be 14 ways. And for the rest of these guys, you can just kind of add them up. 34, 35, 20. Now, the question states, how many ways are there to reach the other side? So there's 14 ways to get to this side, 34 ways to get to this side, 35 ways to end up here, and there's also 20 ways to end up here. So all we have to do is just add all these numbers, and that will give me the total number of ways to reach the other side. All right, so add them up together, and we get 103 ways to get to the other side. All right, let's take a look at another problem here. In this problem, we have Jack again. Jack can only travel east or south to get to work. So this is his home at point A, and I guess work will be here at point B. Given the following obstacles, how many pathways are there from A to B? Okay, so let's take a look at these obstacles. We have a flood. Okay, so there's my flood. So what that means is I can't go through this point right here. I have an accident. I have an accident over here, so that means I can't go through this point over there. And I have a nuclear bomb, which is interesting. Okay, I got a nuclear bomb over here. So I guess that means I can't go through this point, this middle point right there. And is that it? Are there any more accidents? Maybe not. Okay, well, let's start. So if Jack is starting at point A, he can definitely move down in the south. That's one way from here to here. Now Jack can also move to the east, and there's one way to get there. So once again, this is looking very similar to Pascal's triangle. 1 plus 1 will be 2. And now there's one way here, there must be one way there. 1 plus 2 is 3. One way down there. Let's work over here now. If this is 1, this will be 1. 2 plus 1 is 3. 3 plus 3 is 6. If there's 1 here, there's 1 over there. 3 plus 1 is 4. 6 plus 4 is 10. 3 plus 1 over here is 4. 6 plus 4 is 10. Now this point's still okay. We just can't go through this point in the middle here. And then 10 plus 10 is 20. Okay, great. All right, now if there's one way over here, then there's one way over there. 1 plus 4 will be 5. If there's one way over here, there's one way over there. One way over here, one way over there. 1 plus 5 is 6. One way over here, so this will be 1. 1 plus 6 will be 7. Now what about over here? If there's 6 ways over here, and if I want to get to this point using the same theory from the previous questions, this point will also be 6. And then 7 plus 6 will be 13. And once again over here, this is 20, and to get to this point, there's only one way to get to this point, and that's by coming through this part right here, so this has to be 20 as well. 20 plus 6 would be 26. 13 plus 26 will be 39. Now let's work on this side of the map. If there's one way there, then this will be 1. If there's 10 ways here, then this will be 10 ways. Once again, we're going to avoid this middle spot there. If there's 20 ways here, then this will also be 20. 26 plus 20 will be 46. 39 plus 46 will be 85. One way over here, so there's one way over there. One way over here, so this must be one way. 10 plus 1 will be 11. 1 plus 1 will be 2. 11 ways here, so this must be 11 ways. 11 plus 2 over here, this will be 13. And 11 plus 13 will be 24. So we're getting very close to the end of the problem now. 20 plus 11, this will be 31. 31 plus 24 will be 55. 46 and 31 will be 77. 77 and 85 will be 162, I believe, and 77 and 55 will be 132, and when you add that number and that number, you're going to get 294 ways. All right, so that was a very good problem using Pascal's triangle. All right, so that concludes the lesson on Pascal's triangle. So in the beginning, we were trying to make some relationships between the triangle and combinations. But more importantly, I think for this chapter, Pascal's triangle will be very useful for some of the pathway problems, and we will also use Pascal's triangle for the next lesson, which will involve the binomial theorem. All right, so we'll see you in the next video.